And hello,
Hello.
And welcome back to...
OPS Live.
We're coming to you live from San Diego, California, where it is gloriously sunny out and people are getting sunburns.
And in a feat of technology never attempted before, we are also joined live from San Francisco, California, by my colleague, Josh. He's right there.
Hello.
Hi, Josh. Thank you for joining
Hi,
us.
Liz. Thanks. Glad to be here. Now, you can see me, I can see you.
Yep.
Question is whether I can present a screen.
Well,
We're about to find
We're
out.
about to find out.
And if not, you can vaguely direct me, because what we do have is the ability to share my screen, and I can pull up things from the OpenTelemetry Go repo, for instance.
I think he has some slides, but we could, if we need to, we can like pull the slides up on another computer here, and then you can just tell us when to advance.
So I have installed the extension, and it says I need to allow Rendezvous to access my camera and microphone, which I've already done. That's a little discouraging. It doesn't seem to be working.
Okay,
Perhaps
let's just send me the link, or actually I have the link, right?
You do. I gave it to you last night.
Yeah,
and
I'm going to send this to Liz, and then
Yep, and we'll get it
she's going to open it, and then you can just tell us when to advance things.
You are going to need to grant me access.
I think I just turned on link sharing.
All right. You turned link sharing on to lightstep.com probably, and not to World.
Will you just request access? Will that work?
Yeah, I just did, so you'll have to grant it.
There
In the
it is.
meanwhile, we should probably move Josh's screen to the lower right-hand corner.
Yeah, I'm just trying to flip this around, right?
Ah, even better.
Okay. And then we'll put Josh down here.
Perfect. And send that live. I am still seeing access denied.
Allow external access. Bam.
Bam, there we go.
All right.
Cool.
Let me... Do I need to make us smaller? Hold on, let me shrink us real quick, too.
This is amazing technology.
I guess we're technically covering up the LightStep logo in the lower right-hand corner, but the
Okay
LightStep
with
logo
me.
in the lower right-hand corner is there. Like, thank you, LightStep.
It's fine. Let me just... I'll shrink Josh a little. Or actually, I could just put him...
Well, while you're talking, maybe I'll introduce myself.
Yeah, go for it.
I am an engineer at LightStep, and I've been here for some years. Before that, I was at Google. I've worked on tracing and logging, and this was my first real foray into metrics. It's been a quite exciting time. And so we're going to talk here about the designs that we came up with, starting with the original open census design for metrics, taking into account some new requirements after OpenTelemetry started, and then we'll see where we landed. Are we able to turn the pages now? Cool. So great. So here we are looking at, so I'm going to talk about the OpenTelemetry guidelines. Just to review, this is basically summarized from the OpenTelemetry specification library guidelines, which were written a few months ago. The major guideline that we start with is to decouple the API from the SDK. And what this means to us is that we're going to have instrumentation written in your program or your third-party library, which links against only the API, the pure API. And then the operator of the system, which will be somebody who controls the command line or the environment, the link options, or maybe the main function of your program, is going to choose and configure the SDK. And we need to maintain this separation so that all the vendors who want to provide extra fancy SDKs, for example, are able to do so. And at the same time, we'd like to provide a default SDK, which provides most of the common functionality that we think that we want, and makes it so that most users will be able to adopt this OpenTelemetry library and get up and running really quickly. So if you're familiar with open tracing, we started out with a decoupling of the API from the SDK in that world and didn't have this SDK concept, the default SDK concept. So there's quite a bit that's new in this. I put this diagram on the screen here with diagram was written for tracing, so you can see that, but it's basically the same picture for the metrics API. You've got your user application and the third-party libraries linking against the API. The API might be configured with nothing, in which case you get this minimal implementation. Sometimes that's called the no-op implementation. And then it's coupled with, unless it's got the no-op implementation, you're coupled with an SDK, and that has some functionality related to processing data, and then some related to the protocol that we're going to export in. So the guidelines say that we should try to do some processing in common code. We want to be able to reuse much of the SDK for different types of application that we encounter. The ideal is that new exporters can be written with very minimal effort. And to this, and we're going to try to provide some extension points that let people come into that SDK code base and add something to it, perhaps to be able to implement new functionality without rewriting an entire SDK. The guidelines are also that we're going to include standard open source exporters for the open source systems that consume this type of data. And we want to be high performance, low impact. Those are sort of vague, but we know what they mean. We want to make sure that we don't impact the application too much, don't take up too much memory, and so on.
The other exciting thing about this, by the way, is that the OpenTelemetry SDK now can be updated separately from the API, right? So people can compile against an older API and still have confidence that it's going to work with a newer SDK.
Right. The API should be pretty stable at this point, or at least by the time we get to 1.0, it'll be very stable. And we should be able to swap in a new SDK or link against a new SDK against an older library version, as you say, API version, as you said. So let's move to the next slide. Let's see what we're talking. I want to talk about what it means to decouple an API. So now, since the API is independent from the SDK, what we came up with is that we need to define the semantics of the operations. And I'm trying to compare this with this term of a facade API, which is out there. You see these in the diagnostic space as well. There's often like a library for logging with a facade on it. And the reason why that decoupling is not the same as creating a facade API is that we need semantics so that we are going to tell the SDK what it means when we make one of these operations on a metrics API. Instead of saying what behavior we want to happen, what operational behavior we want, we're going to say what it means. So the semantics let the instrumentation convey meaning, and it also lets humans read and understand what's happening. And then the SDKs, which are, again, decoupled, are going to be able to implement their own functionality that are matched to the semantics of the operations. So just to give an example,
we might want to define export.
Well, a Prometheus histogram, or any histogram really, is going to be when you have a number of measurements, you're going to construct different ranges, usually contiguous, that are going to, and we're going to count the number of measurements that fall into each one of those ranges. So if you were measuring latency, for example, you would have a range that was like 0 to 10 microseconds, and you'd have a range that was 10 to 20 microseconds. And then as those ranges get higher and higher, you might make them broader, or you might not. That's another one of these behavioral things that you can usually configure. And so in a Prometheus API, or even in a StatsD API, you did have a method that said histogram, here's my measurement. And what we're trying to say now is that because the SDK is decoupled from the API, we're not going to say create histogram anymore. We're going to say I am recording a measurement. That is more of a semantic definition. It gives meaning. It says what the SDK is able to assume about that event, or what it ought to be able to do with that information. And so this is actually a pretty significant departure from the sort of existing metrics libraries. And I'm going to keep talking about this theme. One of the reasons why we don't want to have, one of the reasons why it's important in a diagnostics library that we are giving semantic definitions and not really sort of operational definitions is that most of these APIs are write-only, in the sense that you don't get to read back anything from the diagnostics API. So you're not reading anything back. You're not getting anything from the SDK. So it's hard to say what what you mean when you're telling it operationally what it should do.
So effectively, kind of from an API design perspective, right, like what's happening here is the storage format is not being specified because that's a thing that can be optimized later, whereas the upfront thing that people want to record is just, hey, I've had a RPC that took 30 microseconds, right? So it's, as I'm understanding, this is kind of the motivation is kind of not over constraining the storage format at the time that measurements are recorded.
Right, and if you're familiar with, say, a Prometheus library, you'll know that there is a histogram type. There's also a summary type, and those two types, those are what we call value types. Those are the output of the system when you enter these measurements. Those are semantically the same type, and we are going to collapse them into one metric type, metric kind, I call that, in the API here for OpenTelemetry, because they have exactly the same meaning. And whether you choose a summary or a histogram depends on what you want, but also it depends on what the SDK itself is able to do. And there's all kinds of optimizations and cost concerns and trade-offs that you can make when you're deciding which one of those that you want.
And that starts eventually looking more like an exporter's concern necessarily rather than a property of the ingest time. So this all seems to logically make sense to me.
Great. Yeah, that's exactly right. So the exporter is going to end up needing to decide what to do there. And we do have some open questions about how to configure this behavior for existing systems or for even current systems. Whether you want to...
Before we go on, can you define what summary stats is for people who don't know?
Yeah, right. So a summary in these traditional metric systems are a summary of quantiles. So if you consider the set of measurements to be a probability distribution, if you will, the probability that the value is less than some, say, 30 milliseconds or 30 microseconds might be 10%. And then so the 10% quantile of that distribution is 30 milliseconds. And then you might often we're interested in knowing what the 50% quantile or the 90% quantile, the 99th% quantile, and so on, 99.9. These are numbers that tell us what's the sort of probability that you were less than a certain maximum value. And so often a summary is that's what we call this. It's a set of quantiles that have been exported. And I'm going to get to this later in another slide. There's a range of performance trade-offs that you can make when you're computing quantiles. And that's another reason why we want to kind of decouple the API and the SDK here, is that different SDKs are going to bring different tricks and algorithms to this space, and they'll be able to do different things. Sometimes you do want a histogram, and sometimes you really care about quantiles, and the capabilities of the SDKs are going to be different in computing this information.
And often it may wind up being, especially if you're combining metrics and traces, you may want to attach the individual metric measurements to events that you're sending out through the tracing API, right? So it's kind of this thing where the more flexibility you give on the SDK side, the better it winds up being, rather than over-constraining and pre-aggregating.
Right, that's a really good point. When we come to talking about combining tracing and metrics into a single sort of product experience, there will be definitely a call for SDKs that are able to export metrics as part of a trace, and that requires a fairly different type of aggregation potentially. Or maybe you're interested in exporting raw data. So again, there's lots of freedom that the SDK has now to decide what to do with these events. Let's take a look at the next slide, since I needed to define what an event is. All right, so I have given four sort of the most important definitions here for talking about metrics. I want to say up front that the term metrics itself is actually dangerously ambiguous, and I try to not ever use the word metric by itself or metrics by itself. So the term that I'm using here to talk about the thing programmation, depending on the type of metric instrument that you have, there will be different ways to do that. And these are defined in code. You declare them by allocating them with a constructor. I'm going to give an example of that on the next slide, or 2 slides from now. So once you've allocated these in your program, you can operate on them and to report numbers, essentially. A metric event is when you actually call one of these instrumentation statements that updates a metric instrument. So the event will be, I'm adding to a counter, for example, and the semantics of the API say what it means to add to a counter. You're going to compute a sum. You've added one new value to that sum, for example. The term metric labels comes up very often. One of the most powerful things that we are able to do with labels in the metric space also refer to them as key value pairs sort of generically. These are additional dimensions or categories that are associated with the event, and when you're analyzing your data, you often will slice or roll up by these values, for example. So labels are one of the major features of the API, and you can attach them to these events, and we'll get to talking about the ways that you do that later. The word aggregation is hard to avoid here as well. It's pretty important to understand that metrics events are quite expensive if you were to record them individually and literally send them out over the wire at once, one-to-one. So very often we make an effort to optimize the performance of the metrics API by aggregation. And there are two types of aggregation that we will end up talking about. The first and most common is temporal. So let's say you have a minute worth of data and you're aggregating a counter. What you're going to do is you're going to compute that sum over 1 minute, let's say, and then export just one value at the end of the minute. And this lets you export a single value instead of all the events that were contributing to that sum. When it comes to talking about labels, once again, we may be interested in aggregation over label values. And so the term spatial aggregation comes up. We think of these labels as additional dimensions on the data, and so the term spatial aggregation applies because each value for a dimension or a key value is some part of that dimensional space. And when we do spatial aggregation, we're dropping dimensions in order to collapse data into a smaller space. So this is what happens when we combine values into a fewer number of label values to get less data to export.
So for instance, one of the things that we used to do when I was at Google, for instance, is that, if you had a number of different hosts that you were running a binary on, you might choose to define a taskless aggregation to say, I don't care which host it came from, all I care is which data center and which job name, right? So you're dropping that dimension and combining them all together and saying, you know what, this counter, right? It's 5 from the host A, 6 from host B. Guess what? This is now just 11 from that data center and from that binary.
That's right. And this can be done either in the process as you're exporting data. And you might ask, why would you put on values on a metric that you're not going to export? We'll get to that a little bit later. But definitely in the case where you're aggregating data from multiple machines, if the machine is or the host is one of the attributes that you have, you might end up wanting to drop that in order to look at a single value. Okay, let's see. The next slide here talks about the 3 kinds of instrument that we have. Again, these are the semantic kinds. Each one of these has a different meaning, and each one of these supports just exactly one operation. So the 2 that are most familiar to you, if you've dealt with many of the existing metrics APIs, are going to be counter and gauge. Counter has an operation named add. And usually the meaning of this operation is that you're going to contribute something to a sum or a rate. And that is actually I'd say the most straightforward of these metric instruments. You're computing a sum and you're going to add values to it. You may add one value, or you might add one value that's 10, or you might add 10 values that are 1. It doesn't matter because the semantics are you need a sum. Mm-hmm. And so counters are the easiest to aggregate temporally, especially because you can do them with a simple atomic operation. If you have a counter in memory and you want to add to it, you just add it and that's it. The gauge instrument is a little bit more difficult to understand. Usually you're using a gauge when you want to have a current value. You might have a current value because there's some complicated piece of code that you aren't responsible for that computes it for you. So instead of updating individual changes, you're going to periodically look at the current value and set it. That way the metric system is able to export it and able to use that in its reporting.
Or the more prototypical case of that is something that's even completely outside of your control, right? Something like the CPU utilization on your host, right? Where it has a current value. You can look up the current value, but it's not necessarily something that gets changed by your code.
Right. So load measurements, for example, that's exactly the most canonical example, I'd say, CPU load. And the final type, the semantic type here is called measure. So we call them measure metrics or measure metric instruments. It has an operation called record. And the semantics are that you're entering an individual measurement. And that's unlike the other 2, where the number of calls to count or add or the number of calls to gauge set are not important. You really only want to know the sum or the current value. But with measure metrics, when you're recording an individual measurement, the number of measurements matters, as do individual values. And these are the instruments that we use to report quantiles, summary values, as we called them earlier, or histograms. And these are the ones that can get expensive because you might need to actually record every raw value in order to compute an exact quantile, for example. And we're going to talk later about how there are ways to compute estimated quantiles that are significantly cheaper. And there's certain like very cheap operations you can compute like max and min that don't require much at all, but that's much less information. So there's going to be a configuration or a range of performance approaches for these aggregations on measure metrics.
I think we have to stop and reinforce here really quickly, like the difference between counter and measure again, right? That a counter might say, might measure how many requests per second am I getting by measuring the cumulative sum of how many requests I've received since the process started. Whereas the measure actually takes an additional attribute, right? Not just, hey, I'm incrementing the number of requests by 1, but instead actually saying, hey, in this request took 30 milliseconds or 30 microseconds to compute, right? So instead of just recording, did something happen, yes or no, instead it's recording something that you may want to bucket or otherwise segment afterwards.
Yeah, the way I think of it also is that the number of calls matters in this case. So you're interested in the count, whereas the number of times you called add doesn't matter. That all that matters is a sum. But if you call record, you're not only giving a value, you're saying one event happened, because you might be interested in the rate of events independently from the distribution of quantile information, for example. Now let's move on to the next slide. I have an example here of how you allocate an instrument. So we've talked about the 3 instrument types, or the 3 kinds of semantic instrument here. Each kind supports integer and floating point instruments. So that gives us basically 6 constructors to begin with. I've shown this example here, and I want to declare that I am skipping over a very tricky part of this whole OpenTelemetry API SDK discussion, which is how you deal with global variables or program initialization. It's pretty different in each language, so I left it out. But in this example, we're taking this variable named meter, which is the SDK essentially, and I'm saying new int64 counter. So I'm telling you I want a counter. Its name is bytes.indexed. I've said a couple of options here. One is named with keys. And the result of that is that I have an instrument, and I can call add on this instrument. The with keys operation turns out to be pretty important, and I'm going to discuss it in a later slide. Not true, I'll discuss it right now. The idea of with keys is that now we've decoupled the API and the SDK, so we're not telling the SDK exactly what to do or what operational behavior it should have, but when you do declare one of these instruments, the SDK is going to want to know how to deal with it. And very often, we need to have aggregation in the process in order to get good performance. So if the SDK has no other configuration, if it's a fairly simple SDK, or you haven't given it any configuration, with keys here serves as an advisory way for the programmer to say what you should do with this metric. So given no other information, the good default here is probably to take the keys named project and protocol in this case, and use those 2 dimensions to pre-aggregate the data. Again, though, this is just an advisory call, and that's because we've decoupled the API. These are good defaults, but the SDK is still free to do anything it wants. The SDK could override this configuration, or it could do anything it wants. Okay, let's continue now. The next slide talks about optional restrictions. We have described exactly 3 types of metric instrument, the counter, gauge, and measure types. Try to call them kinds to avoid the word type, actually, sorry. And each of these has a default behavior. When we looked at the existing systems and the types of use that you have for these instruments, we found that there are definitely, in each case, one fairly common but less common alternate behavior. So let's talk about counter, for example. The default behavior for a counter is monotonic, and that means that the values that you add to it have to be positive or 0, non-negative. And This is useful because very often with counters, we want to compute a rate. And if you're counting negative values, it defeats the value of a rate calculation. So if you declare a counter, its default behavior is to be monotonic. It means it will, the SDK should reject a negative value, and you're able to then compute a rate. The alternate behavior in this case is non-monotonic. If you want to compute a count, but you're counting positive and negative values, then you would declare the alternate behavior by saying, I want a non-monotonic counter. And the SDK will then accept your negative values and will allow you to have a sum that rises and falls. One of the canonical examples of this is you'd like to count how many bytes a particular data structure is using. And every time you allocate, you're going to count a positive value, and every time you deallocate, you're going to count a negative value. This lets you compute sums, but you can't compute rates using a non-monotonic counter. In the case of a gauge, the default is non-monotonic. This is a little bit of a tricky definition. A non-monotonic gauge just means you can give it any value you want. We use this monotonic gauge to describe a gauge that can only rise. So when you set the next value, it should be higher than greater than or equal to the last value that you set. This turns out to be fairly important for the Prometheus system, which has traditionally dealt with gauges, monotonic gauges, as a way to reflect a counter. And so we've preserved this behavior. If you have a value that is exported, but is not something where you're, again, able to, you're not actually receiving individual events. It's another thing that you're observing, like CPU load. Let's talk about CPU usage. This is a value that only rises. You don't get to compute it, but you can read it once in a while. So you might have a gauge that says CPU usage. It will be monotonic because your CPU usage never falls over the life of a process. So that's a good example of a monotonic gauge. So lastly, the measure instrument has default behavior of absolute. That means that by default, we expect values are going to be greater than or equal to 0. This is standard behavior. It's probably the more common that we found out there. One of the advantages there is that you can use a measure to compute a rate, again, just like a counter, if all your values are positive. This allows you to compute the count and a sum, which computes a rate at the same time. So you might be interested in knowing how many requests were there and what was the rate of bytes, let's say. So if you're recording the number of bytes per request, you could calculate the rate of requests and the rate of bytes. Now, the non-absolute measure is provided for the opposite case, where you don't have to require positive or negative or 0 values. You might have negative values. These are cases where, I don't know, you're measuring temperature in Celsius and the values are simply negative. So you'd like to have a measure that supports negative values. All right, let's go on to the next slide. Now, here we're going to start to talk about performance. We're still talking about the API, but a number of factors related to performance have entered into the API, and we're going to try and talk about those next. So we've talked about temporal aggregation now a few times. This is the primary tool for controlling metrics costs. And it's fairly simple in the case of a counter or a gauge. If you have a counter and you have a number of count events or add events, that is, you add them into a current sum, you're only going to need to export the current sum once in a while instead of exporting all the individual counts. With a gauge, it's similar. You can record the last value of a gauge and export just that. So if you have 100 calls to gauge set and you want to export the current value, you don't need to export 100 values. You can only export the last value. That's the semantics of the gauge instrument. So there are two major cost concerns that come up when we deal with metrics APIs. The first is labels. Metrics labels are going to be expensive, and we'll talk a bit more about this. But the intention of having labels is that we're going to aggregate them independently. So if you have high cardinality in your label set, you may end up occupying a lot of memory to store individual counts. Those individual counts are temporally aggregated, but you have to maintain them independently. And so you might end up filling up your memory with lots of different counters if you use too many label values.
Can we use an example for that? Like, for instance, if you had individual user IDs, even if one user hits you once, suddenly you have to create and track the label set, even if the values are all 0, right? And you would have to keep that ad infinitum until your process restarts. So that's kind of the reason why we say that high cardinality metrics are very difficult to achieve.
Well, I think I want to slightly change what you said. We don't really need to keep those in process for the entire process lifetime. That might be a requirement for some exporters or for some systems. But at the very least, we're going to have to construct a temporary value that maintains that count for each user ID. And if you have 1 million user IDs per minute, you might have to maintain 1 million user ID counts and then export 1 million user ID values at the end of the minute. And that alone could be very expensive. And then with metric instruments, as I've sort of said already, to compute an exact summary with all your quantile values, you may actually have to compute that from all the data. So you could have to record all the data and then compute quantiles, or you might have to compute a fairly expensive algorithm that approximates or exactly computes these on the fly using a stream algorithm. So measure instruments are generally going to be expensive no matter what you do, and we'll look at some ways to control those costs as well. Okay, let's move on. The next slide is talking about calling conventions. These are some of the ways that we address cost. So if you're familiar with existing metrics libraries, you may know about Prometheus and you may know about StatsD. The theme here is that we kept coming into as we design this API is that users who come from Prometheus are going to expect the certain calling pattern that they've become familiar with, and for that, they get pretty good performance, but they may be restricted in terms of labels. This bound instrument calling convention is one that's much like Prometheus. You have an instrument, you're going to bind it to a set of labels ahead of time. This gives you a bound instrument, which you can then call quickly to say add or set or record on. So you pre-declare your labels, and then you get this thing that you can use to very quickly record a metric or very quickly add to a sum or very quickly add to a gauge. You've done a lot of pre-computation in order to make this fast. If you come from the other side of the world, StatsD, for example, or if you have a case that's just not something you're going to reuse, it might be a status code that's just sort of like random, you don't know that you're going to reuse it, it happens in the moment, you're just going to make a single call. So this is called the direct calling convention. In this case, you just have the label set, you have an instrument, and you have a value. You're going to call it once. This is much more like a StatsD instrument. These two modes are the sort of primary performance control that you have. If you can pre-compute your labels and pre-allocate your bound instruments, then that'll be much faster for you. But there are cases where you can't, or there are cases where it's simply not convenient to do so. So that's the case when you end up using direct calls. We have a third calling convention called batch. You call batch record on the meter with a set of labels and a set of instruments and measurements, or values, that is. So you can say, I have this label set. I'm going to update 5 metric instruments all at once. I've got some examples of these on the next few slides. So let's talk first on the next slide about reusable label sets. It turns out that the most expensive aspect of dealing with metrics is simply constructing and manipulating sets of labels. So if you're going to do aggregation by a set of labels, very often inside the SDK, you need to look up something based on that set of labels. And labels are going to be either a list or a map from key to value. And very often in a programming language, you cannot use a list or a map as a key in another map. So there's some computation that we need to do in order to get from our set of labels to a thing that's like an entry in my SDK that's going to contain temporal aggregation or for that particular entry. And this turns out to be the highest cost of dealing with metrics. Whether you're using the bound instrument calling convention or the direct calling convention or the record batch calling convention, it's most expensive to construct the labels in the first place. So,
which makes a lot of sense because you think about garbage collected languages where we're constantly creating and destroying these things versus just reusing them consistently.
So the thing we've done here in the API is to create a way of telling the SDK, I have a set of labels, please do something with that and give me back a handle that I can use again and again. You may not end up using that again and again, but at least you're handing this to the SDK. And if you do end up using it again and again, the SDK is able to perform a single computation, for example, to encode a string representation, maybe, that it can then use every time you use that set of labels. So this optimization applies to all the calling conventions. You can use label sets in every one of those cases, and this makes it possible for an application to lower the cost of metrics by planning ahead, essentially. This, it turns out to be a fairly significant optimization. If you're using the bound instrument calling convention, it's not so important. Let's turn to the next slide and see an example. In the bound instrument call, you have a set of labels that we allocated using the call in the previous slide. You have a bytes index count instrument that you've allocated. And in the example here, you say bytes index count.bind. You hand it the label set. This gives you a bytes indexed count bound instrument for this request because we're supposing that the labels are matched to this request. Now I have an example here of a loop where you're going through those list of values, and for every value you add to the current bytes indexed using the bound instrument. You don't have to pass the labels again and again. It was still expensive to compute that labels once, but at least the set of labels once, but at least you're going to amortize that cost using a bound instrument. I confess that this is a little bit of a contrived example because you wouldn't perhaps need to call this RIC bytes indexed add on every loop iteration. You could compute a total and add it once because it's a counter in the example. But if you were using a measure instrument, this would be pretty significant. So you'd say record the value of, if you wanted to compute a distribution or a histogram or a summary of the size of bytes indexed, you would then use a measure instrument and you would record each size. At the end of the loop, you would be done and you would only serialize that label set once. So that's the benefit of using the bound instrument. So this would be a very fast call in this case. Sometimes it's not convenient to use, let's look at the next slide. Sometimes it's just not convenient or to use one of these bound instruments because maybe you don't have anywhere in your program to store that state, or it's deep in some library call where you can't make that optimization, for example. In this case, you're going to simply call it directly. So I've summed the value of this size, computed a total, and now I'm calling bytes index count.add. I'm using a Golang example here, so we've got a context object. The total is the sum that you computed, and then labels is passed once. So this is much easier, much simpler. You don't have to allocate any state and hold on to it. You're just going to call directly onto the instrument. So next slide, I have
is the context a full OpenTelemetry context that may contain other labels that we may not necessarily have explicitly passed?
Yes, and I have a slide about that later. If you were not dealing with Golang, you would pass an OpenTelemetry context. The Golang context hides that for you, but it's the same idea. In the context, there are going to be distributed labels. We'll talk about that a little bit later. So in the next slide, I have one more example of the batch calling convention, just to make the three calling conventions clear. If you have a single label set and several measurements that you want to update, you can update all the instruments at once with a single record batch call. This may be faster, for example, if the SDK is going to take a lock in response to a record batch, then you might be better off doing this once instead of once per instrument. Otherwise, it's roughly the same as calling those instruments 3 times, calling each of those instruments once.
So to use the example of when people might use the record batch, right? Like often if you're writing an RPC handler, you might want to record the number of bytes indexed, the number of milliseconds the request took, the increment the success counter, increment the total number of requests received, do not increment the errors counter, and so forth. And those all will share the same labels. So it's kind of an occasion at the end of the request to just do this batch call.
That's right. That's a very common example, actually, is at the end of a request handler, you're going to update 7 or 17 metrics, and you've got one label set. This is, again, an example where the optimization of computing a label set may not be super important, because you're going to compute that label set once and use it for all those metrics. You could, and it may not be much more efficient than calling 17 metrics updates all at once, but this is also a convenient calling pattern for your code. You don't have to call 17 times and so on. All right, let's look at the next slide. We're going to talk about label sets a little bit further. I mentioned earlier that if you're going to export some data and you're going to perform spatial aggregation, why would you bother putting those labels into the label sets in the first place? Well, one answer is that the SDK might override your configuration and decide to export all the labels. And this is pretty common in certain statsd usages, to just apply any label you want, because there are good reasons to do that. You can record that information, and then you have a lot of you have the ability to go backwards in time and look at labels that you never thought you might use by looking through your old metrics data. So the default SDK provides this recommended keys. This is that advisory thing we were talking about that lets the programmer declare what keys they're interested in by default. And the SDK is able to do whatever it wants. So when the programmer puts more labels into the label set than are actually being aggregated, whether it's because recommended keys are being taken or whether because the SDK has decided for its own reasons which labels to aggregate by, you end up having what we call additional labels. The additional labels are there and they get spatially aggregated away when you do export. So you may ask, why do we want them in the first place? And the answer here is that SDKs can export a lot more data than just the pre-aggregation. So one of the common applications is to export samples. You'd like to, sometimes these are called exemplars. So you can export, in addition to the pre-aggregated data, you can export sample data that might be individual points in that metric update to say not just the dimensions that were aggregated, but all the dimensions that were present. And this might be helpful for debugging or like looking deeper into the data.
For instance, if you have, if you've chosen to aggregate away client, but you wind up having, a bunch of very slow requests that all are coming from one client, if you have those additional labels, even if you weren't explicitly aggregating by them, you'll get that data, which is super helpful.
You could. SDKs are going to be able to do this. So one of the things you can do is try to provide distribution information about clients. Although we are computing an exact aggregation by the dimensions that we're exporting by, you might be able to additionally report approximate distribution information about the other dimensions. So that would be an add-on feature that some SDK could apply. And then if you're talking about tracing integration, one of the powerful things that you might be able to do, for example, is ensure that a trace is collected for every value of some secondary dimension. So if you do have, let's say, a user ID, and you're not going to include that user ID in the aggregation, but you know that you had 100 user IDs in this minute, maybe you can arrange to compute one trace for every user ID without exporting the user IDs in the metrics stream. So this additional information provides ways that the tracing and the metrics SDKs can work together to export more information. All right, hope that made sense. Let's move on to the next slide. This is the one that you asked about earlier, Liz. The context argument that's passed to every one of these calling conventions does contain the OpenTelemetry context, and this includes distributed context, or what we call correlation context. These are label values and key values that came from parents in a RPC hierarchy, for example, or the parents in a trace that were passed down and propagated through calls to the current span, let's say, that are available. So the default SDK does not automatically use this information. It's certainly something that a very smart SDK could use. There's a lot of cost concern here. So we've taken the fairly simple approach of saying that the default SDK will not automatically apply distributed correlation context, but the user is able to extract that information. I haven't included an example of it here, but the correlation context API provides a way to ask what's the value of this label in the distributed context. And you can then put those into a label set and use them on your metrics, for example. And this would be an example of one of the sort of early use cases for distributed context propagation, including correlations, was exactly for this, to be able to do real-time aggregation in the children of your trace by some value that was provided by the parent. So let's suppose that you want to count the number of bytes that are being read on a disk at the very bottom of your RPC hierarchy. And you want to count them by the user that's making the request all the way at the top of your hierarchy. What you'll do down at that disk is extract the user from the correlation context and apply it to your metric updates manually. It's certainly possible that an SDK could do this automatically, and you can imagine all kinds of ways to configure this. There's definitely some academic work that talks about how to do this in a sort of clever and automatic way, but we've left that out for now. You can do it you can do it manually. Okay, we're sort of done talking about the API and all the considerations that we put in there for cost control. I want to spend a few more slides talking about the current state of the default SDK and how it's been organized. I'm basing these next few slides on the prototype that we have in Go, which I've been building with a few collaborators. And I'm just going to run through this briefly. I don't want to try and spend too much more time on this presentation.
Because honestly, these are details that shouldn't need to matter to users of the API. They mostly matter to people writing exporters and people working in the SDK.
Right. Earlier on the very beginning of the slide, the library guidelines said that we should provide extension points and we should make these exporters fairly easy to write. I'm just going to run through this really quickly. So the SDK that we've got so far has this thing called a meter. Its job is to just sort of keep track of all the things that are in flight. And that basically is the pairing of an instrument and a label set and any active state that hasn't been exported. This is the sort of front line between the API and the SDK, and this is where you really want to focus on high concurrency. So try to avoid locking as much as possible or hold locks very briefly. After we pass through the SDK, there's this concept of an aggregator. This is the thing that implements some type of aggregation. And I've talked about several types of aggregation so far, and there's another slide to talk about specifics that we have. There's this concept of an aggregation selector. This is a policy that depends on the capabilities of the exporter and the desires of the system or the user configuration that says, what type of aggregation do you want? What's your tolerance for cost? If you want very precise quantile information, you'll choose a different aggregation. And if you want very cheap quantile information, like only the min and the max, you'll choose a very cheap aggregation. So this is the point where we configure the policy about which aggregations to use. Okay, next slide. There's a concept of a batcher. I'm not sure this is the best name, to be honest, but what this type does, this part of the SDK does, is decide about spatial aggregation. Which labels are we going to export? Its job is to reduce the dimensionality by applying spatial aggregation. And then what it does is it computes a set of checkpoints. Each independent metric instrument and label set that will be exported has a checkpoint that's computed by this batcher. And so there's policy here as well that says which labels do you want to aggregate by, and combined with which aggregations, that'll provide all the information to an exporter. The concept of a checkpoint set is just for every active instrument and all the label sets that we're exporting by, you have a checkpoint of the aggregator. And the aggregator defines its own data model because different metric instruments have different data models. So the aggregator for a counter is different from the aggregator for a gauge, and that's different from the aggregator for a measure. The concept of a controller is really just deciding when to perform this checkpoint. If you're doing push-based metrics reporting, you might have a timer set up that says, I'm going to export data every 30 seconds. But some systems do pull-based metrics, so then you're going to have some sort of service that responds to a request and decides when to checkpoint metrics. Each of these is separated in the SDK so that you could swap in a different object to do different behavior. Lastly, we have the exporter. This is all its job then is to take a checkpoint set, which was computed from a set of aggregators and the batcher and the checkpoints, and just formats it and sends it off. So actually very little work takes place in the exporter. And we have current exporters in flight or in the works for Prometheus and StatsD and a standard output one that we use for debugging.
The standard out one, I think, is done.
Yes, that was merged. So that's already there. If you're using Go, you should be able to go check that out.
Which is helpful for understanding, right, like, under the hood, if you're thinking about writing an exporter, knowing what information you can access is super helpful for being able to understand, okay, this is how I need to write my exporter.
Yes, exactly. All right, we're almost finished here. I want to talk a little bit on the next slide about how we aggregate measure instruments. I've listed 4 on this slide. Measure instruments, again, are the ones that tend to be expensive because to compute quantiles, you need all the data. And if you're using less than all the data or reporting less than all the data, you must be approximating in some way. So because there's a tremendous range of costs here, we offer, or at least the default SDK is going to offer several options. The cheapest one that we have is called min-max sum count. The reason why min-max sum count is so cheap is that it requires exactly 4 words of memory per aggregator. It takes O of 1 memory to compute the min, the max, the sum, and the count. You don't have to remember all the values. You just need to compute a little bit of information. And this is actually often all you need. And if I was to choose a default, this would probably be my choice. I think people should probably opt into expensive metrics when they want them and not have that when they don't. So now the next one is the idea of a sketch. This is an approximate algorithm that we can use to estimate selected quantiles. So there are a number of algorithms out there for doing this. In the Go implementation, we've included the Datadog DD-Sketch algorithm. That's pretty recent. There are other algorithms you may have heard of, T-Digest, Q-Digest, GK-Sketch. There's lots of them out there. And one of these will be included. The idea is so that you can have a sort of compromise between very cheap, which is just the min, max, sum, and count, or an exact report, which would include very precise information about quantiles, or even just raw information that would be recording all the measurements exactly. So lastly, there's this histogram, and that's a very specific output. If you want a histogram, you should ask for it. Very often, if you're computing a histogram, you are interested in some exact bin range that you need, and maybe there's a reason why you want that for your system. The problem with histograms is often you need to know upfront what the bin ranges are, and if you get that wrong, your histogram will not be very useful to you. So
there's also this
my guess
lovely
is
trade-off, I think, between histograms and percentiles, where if your histogram bin ranges are wrong, then your percentile measurement winds up in the middle of a bin and you have no idea kind of where in that bin it falls and you have to approximate. So these are kind of all various ways of kind of grasping at the elephant to try to figure out like what shape does it have.
Right. If you know the range and the distribution really well, you might get away with a histogram and it's going to be very accurate for you. You can compute quantiles from histograms, but there's a chance that you're not going to get very much useful information from that. So my guess is that the common application is going to use a sketch or one of these min-max sum counts. And then if you specifically need a histogram, maybe that's what you'll get. Histograms are often configured with either linear buckets or exponential, logarithmic buckets, or even variable buckets, which can be maybe the output of something. But in the terms of an aggregator, you need to know up front what your histograms are. Otherwise, you're doing something more approximate like a sketch. There's an algorithm or a data structure out there called HDR histogram. It's implemented in Java. It's been around for a long time. That's one of the examples of a sketch that you might use. It's computing variable with histograms, in other words. All right, last slide here is talk about work in progress. We aren't quite finished here. There's definitely some work left to do. One of the things that we haven't tackled yet is namespaces. Most of your metric systems out there let you have namespaces on the metric instruments, and we see that as being a requirement, but we haven't figured out exactly what the API should look like. There's some moving parts in the OpenTelemetry specification. There's something called named tracers and named meters that is maybe related or maybe not, so we're kind of still working on that. There's something called an observer gauge. The semantics are the same as a gauge, but it's something where you register a callback rather than calling set explicitly. And there's some questions about what the calling conventions should look like there. But these are actually really important because if it's the case that you have an expensive computation, you don't really want to have a timer that's firing any more frequently than metrics collection. So if you have an expensive gauge and there's no context, meaning you're not going to use the trace or the distributed correlations, you should give a callback, and then the metric system will only ask the current value when it needs it. And that way you save cost. So we see this as being really important, but we haven't pinned it down yet. And then the current SDK that we've spec'd out, or the example that the prototype that we have in Go, really implements several fairly simple policies. There's one batcher that does aggregation by the default keys, the recommended keys that we've talked about, and there's one batcher that exports data by all the keys. And those are the two kind of like extremes that you might have in a simple system, but we expect that real systems are going to end up being much more configurable. So you can imagine getting a configuration from a server that says which metrics do you want, which label dimensions do you want, which aggregators do you want, and so on. So there's a lot of future work in configuration and refining the behavior of the SDK.
Yeah, I think I even asked you about that when I was asking about, hey, which percentiles does a standard out exporter take? And the answer is we haven't done the configuration mechanisms yet.
Yeah, that's definitely going to have to happen. And I think that probably the OpenTelemetry protocol will end up being extended to provide configuration. It happens in tracing as well, where you say, I need to know what my sampling rate should be because I don't know. And so that's a configuration that you'd want to get from a server. So very much likewise in metrics, you'd want to say, hey, I want to push metrics. I don't want you to pull them. I want to know my period. I want to know which metrics you want. I want to know which labels you want, and so on. So I expect that that's coming. And lastly, we're still working on the standard exporters. We've got in the Go repository, which is pretty far ahead of many of the others, we are working on Prometheus and StatsD. I know that there is work in some of the other libraries, other languages. So Python has done some work in metrics. JavaScript has already got a Prometheus exporter and so on. So we're making a lot of progress, and that's where we are. And that's the end of my presentation. Thank you all very much.
Thank you for coming on to
Thank
this.
you. Wow.
I guess one
Thanks,
question
Liz.
that
Thanks,
many of
Jonathan.
our visitors may have is, how does this relate to open metrics? Kind of how does this relate to the Open Metrics project, which is also a CNCF sandbox project?
Great question. I've been talking to at least a few folks from the Open Metrics project, trying to figure out where these line up. So Open Metrics will describe itself as an exposition format, meaning it's really meant as data transfer format between your exporter and your system. So Open Metrics does have a summary type and a histogram type. So we're still going to have to configure what export do you want? Do you want the histogram output or do you want the summary output?
Mm-hmm.
And so Open Metrics will make a great data transfer format, I think, one day. I'm waiting to see the RFC that they're working on eagerly, actually. I was thinking that they were going to have this by KubeCon, so maybe it's out there, but we're waiting to see that. OpenTelemetry is also working on its own metrics transfer format, which is part of this OTLP protocol. It's structurally very similar, so we're still working this out. I think that these two protocols are going to be very similar. I like the Open Metrics format because it's text-based, and actually text can be a really fast encoding, much faster than protocol buffers in some cases. So I think it'll make a good protocol. It needs to be specified, and I'm waiting to see the current draft.
Yeah, that's super exciting and is super helpful for clarifying these things, especially as we get into the process of going through incubation soon.
Yeah. Well, everyone, we have any other guests coming on, and we need to take a quick production break to try and improve the stream quality. So stick with us. We'll be back in like 2 minutes. Josh, thank you so much for your time today.
Thanks,
really
Austin.
appreciate
Thanks, Liz.
you having
And
on
thank
here.
you for all of your work on putting this code together as well as the presentation.
Yes, absolutely. Thank you so much for everything, for your contributions.
And I think we should point the other SIGs at this. Like, I think that they would find it helpful for implementing
Absolutely,
this.
yeah. No, I
Like,
think we need...
This is the first time I think it's really been explained in one go.
Yeah.
Like, what does this all mean and how does it fit together?
Yeah, someone clip this. I don't think you can.
Yeah,
clip
there's
that
also
much.
an in-flight SDK specification document that it's in review right now. It needs a lot more work, but basically trying to outline the contents of this presentation as a sort of guide for how you should implement or how you could implement this library.
Yeah.
But that's all work in progress as well. Thank you again.
All right.
You're
Thank
very
you,
welcome.
everyone.
Take care.
Take care, and we will
Bye.
see you in a few minutes.